All right, so let's talk about section 2.5 transformations. I was looking at the practice test and the actual test on in MyLab, and it looks like some of the harder problems are skipped, but just in case you're curious, and because the book goes into it, I did want to say sort of in detail a couple of things and like what order you do the things in. They're they're like a couple. They're like two or three correct ways, and then there are like 8 or 9 incorrect orders to do these in, and that's the hardest thing about this. Is if you have the general case where there's 4 different transformations being applied, and you have to keep track of all of them. Well, just I'm going to refer back to this later. We're not going to do the most general case. We're going to do situations where only 1 or 2 of these are being applied, and getting 1 and 2 in the wrong order is the most common mistake. And so we're actually on the test, on the practice test, I looked at it very carefully. I kept refreshing it to see if this ever happened, and there were no problems where there were both of these. So that's the most dangerous thing, and we're kind of skipping it, but you might see it in the future. It's a good thing to sort of look at now if you're feeling motivated, you have a little bit of extra time to tackle a couple of harder problems on the side. But what's absolutely crucial is that we rise to the level of what's being expected right now. So transformations, they're kind of a big topic. They're a little bit finicky. So I want to talk a little bit about, I'm not going to do a formal proof, but we should sort of convince ourselves that this is kind of how these behave. And then if we don't 100% understand everything under the hood, why it actually works that way, well, we still need to be able to do it. So if you just sort of memorize all these different modifications and what they can do to your function, and just how do you deal with one or two of them at a time, then we'll be in good shape. So let's do that. So let's sort of look at a few different ones. So we have let's do f of x is equal to x cubed. I'm going to draw kind of big. I'd like to also have room to put a table on here, maybe, but so what do we got here? So let's go to 10, maybe. Yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You know that x cubed doesn't take long for x cubed to start getting large. So 1, 2, 3, 4. That's -5 is right. Some of these I accidentally drew a little bit too close together, so -5. Let's put it a little bit better, space it out just slightly better. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so it actually starts out extremely flat, and then it starts bending a lot very quickly, and then when you get to 3, 3 times 3 times 3 is 27, which is way up there. So we won't. So the original graph is going to leave very quickly. It's going to leave behind what I've drawn for the axes, and so that's what we got. Okay, so let's start with the stuff that 2 of these are kind of pretty straightforward. So I don't know, let's just do G. So let G of X be equal to actually, let's not do that one just yet. Let's do actually that's fine. Let's do it. Okay, so what happens? You plug in 0. You don't get 0 as your output. Your output gets decreased by 3. I can use a different color here, maybe. Let's try green. 1, 2, 3. So we're at 2, but we're at 1, 1, but then we subtract 1, 2, 3, so we're at -2. We go down 1, 2, 3. We subtract 3 from the output, so it's just. And we go just slightly off. We just go slightly past the last label on the axis, but we get the idea here. And so usually that's the one that works the way you expect it to. It's on the outside of the original function. You apply the original function f. Well, you have to sort of recognize that this is in the form. This is f of the function f of x, but then we subtracted 3 from it on the outside. And if you look at the original pattern, I called that b. So it's vertical shift by b. B was -3 because we have the function f. We have stuff on the inside of the parentheses. We have here a is just 1. It's not, so there's nothing here that actually does anything. And then we add b, which is -3. So started with that one because it's the easiest. But that's what happens. Not too much to see there. We can call this next one h of x is equal to well, what happens? We plug, well, that's a constant times f of x. The rule is if you multiply by a constant on the outside of the function f, then it's just you're multiplying. You stretch by 1/2, which is the same thing as shrinking. So it's a stretch by a fraction is, we've got all these y values. So instead of 8, we're going to be down here at 4. And instead of -8, we're going to be up here at minus 4. So we've got the original function is out here, we smash it, and that's h of x. Okay. I can call this one k of x. This one's gonna be a little bit weird, but we're just multiplying on the. We get the y value. We get the y values from the function f, but then k of x, its y values, is we multiply the y value by -2. So we plug in 0, and then we multiply by -2. We still get 0. But now we're multiplying all the y's from here's the x cubed. We got 1, 1, but now we multiply by -2. We're down here. Multiply by -2. This -8 becomes a -16. Well, maybe, you know, so those first three will give us kind of a rough idea. And if I wanted to go all the way up to this -8, but then I multiply it by -2, I'm at +16, which is basically here. It's not literally vertical, but it's very, very close to vertical. I'm running, it's x cubed is very tall, and then negative twice x cubed is it's flipped vertically, and then it's twice as tall for the same x value. So here we're at -1, but here we're at +2. Here we're at, plug in -2. The original function is -8, but then k of x is +16. All right, so that was, let's sort of review what we did do here. We have this thing, that's this one here. So vertical stretch, if a is negative, then then it's also reflected. But sort of stretching by a negative amount is like reflecting, and then you know, we saw that when you stretch by a fraction, you actually you know, multiplying all the y's by a number that's between 0 and 1, like 1/2 or 1/3, but you know, by a fraction, it actually gets smaller. All right, so it's these two that are a little bit weird and don't quite behave exactly the way you might sort of expect them to, and it just takes a little bit of practice, because inside the parentheses somehow it ends up being the opposite. It works on the x's instead of the y's because it's on the inside of the parentheses, but how do things land in the right places? It turns out that multiplying by c, you end up shrinking, and then when you add d, it doesn't go to the right, it goes to the left. So these are something to sort of pay attention to. And if you ever see a problem in a later class where you have both of these, well, you have to make sure you do them in the right order. If you write it in this form, you have to do it in this order. So that'll be important. But we'll just in this class, it's maybe one or the other, but not both are going to be present. Okay, so yeah, that's kind of a nice graph, but it's getting a little bit crowded. And so let's do the next thing. All right. Now there are a couple ways you can actually do this problem. I'm gonna. It depends on which function's handed to you. Some functions you can't just play with it and turn it into something else. So I'm gonna do it just exactly the way it's written here. And if I try to do more than 4 things, I think 4 is about going to be as the most I can do at the same time on the same graph. Let's do k of x. All right. All right, so this one I want to really, said I wasn't going to prove it, but what I do want to do is I want to examine some ordered pairs, and I want to convince you that these things really do end up where we say they're going to. And there's a kind of logic behind it, but you sort of have to I think I want to go all the way up to like 18 or maybe 20. So actually, yeah, if I count by 2s, then I'm already all going up to 20. That's the idea. So let's. And maybe this also needs to count by 2s. I notice that there's this thing on the inside. So that's a horizontal change of some sort. So let's give ourselves a little bit of space here. All right, so f of x. So we have 0, 0. We plug in 1, we get 2, 4, 6, 8, 10. So this is 2, so half of that. We only end up at 1 when x is 1. When x is 2, we get 1, 2. We get 4. So plug in x equals minus 1 or positive 1. Yeah, so we get 1. We plug in plus or minus 2 for x, we get positive 4 both times. Plug in 3. And we'll get 9, which is right up here. Plug in minus 3, and again we'll get positive 9, and then well, we're sort of combining this with some of the other stuff we already learned about. So eventually we're gonna have to double these. So we're actually, for the very last function, when we have to double these, we're gonna run out of space pretty quickly. So that's about all we're gonna be able to do here. But that's good enough. So this one, I want to do this. I want to think of this as not as 4. You could think of this as 4x squared, which is correct and true. But if I were to give this to you, I would specify, no, I really do want to think of this. I would say do it as a horizontal transformation if I wanted to really make you do it the way we're going to do it. But it's kind of, that's something interesting about parabolas, stretching them horizontally, smashing them in horizontally, well, all this stuff that goes up gets smashed in, and it looks like, and it just ends up being taller. It actually, mathematically, is the same thing as stretching it vertically, which is kind of interesting. So horizontal shrink is the same as vertical stretch. That's pretty interesting. And what I claim is, well, on the horizontal shrink so if I shrink by 2, then it's times 1/2. It's always the reciprocal when it's on the inside of the parentheses and you're multiplying the x. That's how it works. So times 1/2 instead of times 2, you times it by 1/2. So let me do this one in red because perhaps this one might be the weirdest if you haven't seen it before, if it's been a long time. Let me do this one first. So the x value of 2 shrinks it in, it ends up at here. X equals 1 goes to x equals 1/2. X equals 3 goes all the way into x equals, here's x equals 3/2. And minus 3/2, comma 9 instead of -3, 9, as in the original function had -3, 9, and then the transformed function has -3 halves. -3 halves goes all the way up to 9. So let me do it. Actually, I want to explore this just a little bit more just to really convince you. We have x-y pairs. -2, -1, 0, 1, 2. I could do 3 as well. I don't want to do too many of these because it's time consuming. This is going to be a very long video if I do this for everything, but I really want to show you at least one. So this is how you convince yourself that this stuff is true. So what's going on here with G? So G, I claim that we shrunk in the x direction by dividing the x's by 2. So -1, -1/2, 0, +1/2, +1, and if it's a horizontal shrink, then this step, the y's stay exactly the same. But it's a horizontal stretch, so the x's, it's getting a little bit cluttered, so let me just... So let's sort of verify this. So the claim is that this horizontal shrinking rule actually does what it's supposed to. So the people who wrote this textbook, do they know what they're talking about? So let's do that. So G of so for example, this one checks out. That one's totally fine. So plugging in -1 into the function G is the same thing as plugging in the number -2 into the original function F. So that's kind of what happens. It's like you plug in smaller x's, but then the x gets multiplied by 2, and it's like the two things cancel each other out, and you get the same y value. Well, when does it happen? The function G, everything happens faster because you can think of it as everything happens faster, so smaller x's give you the same y. So it's a lot to think about, but if you ever have time, it's the earlier you sit down and you just play around with the numbers and you really transform the numbers, and then you really plug this into the function G and you just sort of admire the sort of structure and how everything has this process and gets shuffled around and then it ends up where it's supposed to. It's kind of a nice thing to do. You really get a better sense of it. But sure, if you just want to do the thing that works, we wrote it down. We said what the rule is. So G is equal to f of 2x then you divide the x's by 2. And that's what happens to all the ordered pairs from the original graph to give you this transformed graph that I drew in red. So multiply the x's by 2, so it's not multiplying the y's, that would be out here. Multiply the x, if g of x multiplies the x's by 2, then you need x's that are half as big to get the same y values back out again. All right, so I don't want to go too deep into this. You could explore the numbers. You could take every ordered pair that I'm going to draw here, and you can verify that h of x does exactly what I say it does here. So what happens? The rule says well, the plus or the minus matters, but it's left. You shift left by -4, which is left and right are opposites, and plus and minus are opposites. So the negative, if you shift to the left by -4, then that's just right by +4. So it's this is f of x plus -4. So that thing on the other side of the board, it's, if you rewind the video, it's all the way to 0. You can see it. You can see that's the other side of the board. Yeah, so moving to the left by -4 that's how negative numbers work. If you do the same thing in the opposite direction. So this vertex is 0.00, 1, 2, 3, 4, and then this one. So 1, 1 becomes to the right. You get 5, 1. You get 3, 1. Then you also get 6, 4, 7, 9. You get 2, 1, 2, 3, 2, 4. What did I say? I said I was going to do blue. Let's actually do blue here. So blue. There's a whole song about that. I'm blue, I'm blue, I'm blue. And yeah, so I'm blue. All right, so we've left it by -4, which is right by 4. And there we have it. So the table, what did I do? I'll write down the table real quick. You can check it. You can go ahead and you can plug the numbers into this function. I'm not going to do the 3s. Same thing happens. You could do the 3s if you really wanted to convince yourself that the pattern really works. But anyways, here's h. The claim was I have to move the x's forward by 4, and the y values are exactly the same for those particular x values. So 2, 3, 4, 5, 6. So 4, 1, 0, 1, 4. See, I plug 2 into this function. -2 squared is 4. Plug 3 in. It's very nice. It just everything really does line up the way it's supposed to. And then some problems are like this. They'll do this, and then they'll either they'll multiply on the outside. So you've already applied the function, and then The new thing is you multiply or add after you've applied the function. So if you apply a function and then you multiply by 2, well, now k is like h, but you've done one more thing. So this is a multi-parter, and so on the homework and on the tests in MyLab, there are ones where there are like 2 steps that you have to do. So what happens is you do an X transformation and then you do one of the Y transformations. This is a Y transformation because it's outside of the function. You apply the function, you start with X's. Okay, on the inside you start with X's, you transform the X's, you apply the function, and then after you apply the function, there's something on the outside, which means you've got y's and you're changing the y's. You're multiplying the y's by 2. So multiply the y's by 2, but this is a Y transformation, so these X's are the same as the previous step. So looks like that. So here, that's h of x, but then we take h of x and we multiply the y values by 2. And here we are. So we take this 4 and we double it and we get 8. We take this 9 and we double it and we get 18. Take this 1 and we double it and we get 2. Take this 4 and we double that to get 8. And finally, when x equals 1, we had 9. We double that, we get 18 again. So all right, so you should probably do a table. You should just include a table. It's like, you should have like at least 5 points, just to be sure. And then just sort of doing it by the table is one thing, and then doing it from the picture is another thing. If you draw a very clear picture and you're very accurate with how you move things, you just think to yourself, what does that mean for the ordered pair? What happens to the numbers? Make sure it gets recorded. And it's pretty good. It's a pretty good thing to check your answer as well. So plug in 2, you get -2. Squared is +4, but then times 2, I get 8. And you could do that with all of these. So it's kind of, if you have those 4 things, let me flip it over again. We're going to do problems where only 1 or 2 of these terms are present. So usually it's like there's an A and a D, and these are not here, or maybe it's like this. But yeah, you look at a book problem. After you do the transformation, be a little bit skeptical. Just actually plug in some ordered pairs, and then, well, where do the x's end up? And then you apply a function at that new x value if there's stuff going on in here, and then you follow up with some stuff that you do to the y's, and you get the inputs and outputs matching up where they're supposed to, like you said. And that's kind of how you convince yourself that these things are true. It's just a little bit of experience. If you do these, but then you test your favorite sample points and go through the whole process of evaluating the function and doing the arithmetic, you will see that what you've done everything will match up. Either that or you made a mistake. So it's a little time consuming because a graph is like, well, a graph isn't just evaluating a function once or twice, it's evaluating a function. There's a whole, there's a whole continuum, infinitely many x values, but at the very least we have to do like, 5 different x values, just to convince ourselves that that you connect the dots and it's mostly on the right track, and then we're good. So time-consuming problems, but put some time in, you'll kind of get used to it, and you'll see what's what. Yeah, it's a pretty big topic, and that's how that works.